So, we continue with the rotational spectra microwave of polyatomic molecules, and I recall that in the case of polyatomic systems we were only looking at the spectra of symmetric tops. And you remember that the symmetric top is one of the special types of molecules in which the moments of inertia have certain relationships. For a general polyatomic molecule, the three moments of inertia about the three mutually perpendicular orthogonal axes all passing through the center of mass of the molecule are in general different. However, the special case when the so called principal moments of inertia, when they are equal in all directions, Ixx, Iyy, Izz, this was called the spherical top. And some examples were given. Cubic molecules and perfectly tetrahedral molecules are the best examples for spherical top. Then we had the special case, namely Ixx equal to Iyy greater than Izz, that is not equal to Izz, and the other case Ixx is equal to Iyy less than Izz, and this was called prolate, and if the Izz is greater than the other two equal moments of inertia, it was called the oblate symmetric top. Both are symmetric tops. The spectrum of symmetric top and the energy levels of the symmetric top are easy to calculate because of the special fact that the Hamiltonian for the symmetric top has a special form. Please remember, for a molecule which had all the three moments of inertia being different, the Hamiltonian is written as Jx square by 2Ixx plus Jy square by 2Iyy and Jz square by 2Izz. And this I did not solve in this course because it's called an asymmetric top. The three cases Ixx not equal to Iyy not equal to Izz is called asymmetric top. And some examples were given in the lecture. And you are supposed to look at the structure of the molecule, and any molecule which has a threefold axis of symmetry will most likely be a symmetric top. And molecules which do not have a threefold axis of symmetry, which have only twofold axis of symmetry, or by nature they are asymmetric top. So there are some special rules. I think I mentioned that in the course. This was not solved, but what was solved was the special case Jx square plus Jy square by 2Ixx when Ixx is equal to Iyy and Jz square by 2Izz. You recall that I wrote this Hamiltonian as I believe it is B J into J square, Jz square. Let me write B J square plus A minus B Jz square. Okay. This was the Hamiltonian form, and for a prolate, this is A, B's are the inverse moments of inertia. 1 by Ixx was related to B and 1 by Izz was related to A, inverse moments. And this, when A is greater than B, which means Izz is less than Ixx, it was called the prolate symmetric top, and A is less than B was called oblate symmetric top. And you had the energy level diagrams written for J square and Jz square operator. You may recall that angular momentum in quantum mechanics, particularly for the molecular system, the components do not commute with each other, and for molecular spectroscopy we use the commutation relation minus IH bar Jz because the axis XYZ are fixed in the molecule. and this essentially means the other components as well, Jy, Jz were minus Ih bar Jx, and Jz, Jx were minus Ih bar Jy. What it means is that simultaneously you cannot measure the x component of the angular momentum and y component of the angular momentum for the same system, but you can always measure the absolute square of the angular momentum and one of the three components, because in the lecture I remember telling you that J square comma Jx is equal to 0 or Jy is equal to 0 or Jz. That is, J square commutes with all the three components, but these do not commute with each other. Therefore, you have this and one of these, and the one of these components was chosen always as Jz, and Jz on the eigenfunction psi j was shown in hydrogen atom earlier and in many other cases to be a h bar m or k. I believe I used the index k, psi j k, and we used k as the quantum number, and the k is the index, which is essentially it's a quantum number which is the projection of the angular momentum onto a chosen molecular axis, the z axis, and k has possible values from minus j plus 1 to j minus 1 to j, namely 2j plus 1 values. The eigenvalues for the symmetric top were Jz square acting on the wave function. Therefore, this will give you k square instead of k. Therefore, the energy for the symmetric top is given by two quantum numbers j and k, and that is b j into j plus 1 plus a minus b into k square. And you can see immediately that k is equal to 0 is a unique energy eigenvalue. It is non-degenerate, one energy state, and that state is called J0, and all the other states plus minus 1, plus minus 2, plus minus 3 all the way up to plus minus k, each one of them will have a slightly different energy because of k square, but both of them will be the same, plus k and the minus k will be the same. Therefore, for all k's not equal to 0, the energy levels are doubly degenerate. And we also looked at the prolate and the oblate symmetric top, and here also it is important to note that the microwave spectrum is possible only if the molecule has a permanent dipole moment. But it is possible that the molecule has a dipole moment in an arbitrary axis, not along the z axis or along the x axis or y axis that you choose. Therefore, the angular momentum, the dipole moment may have more than one component in the respective directions, leading to the fact that there are different selection rules, but all of them will involve delta j is equal to plus minus 1, and depending on the special molecular cases, you may have the selection rules delta j is equal to plus minus 1 and delta k is equal to 0 or plus minus 1. That depends on the molecular nature. We did not elaborate this, but I recall that this was the stated selection rule for the polyatomic molecular case. We looked at some of the polyatomic systems, namely what are symmetric tops and what are asymmetric tops. Some examples were given and some of the energy levels were given, and basic calculations regarding the dipole moment matrix element were also given. With that, I think we sort of completed the basic structure on microwave spectroscopy. We did not move on to the non-rigid molecular system and also the asymmetric top molecular system, because they are slightly more complex, and usually one studies such systems in the next level of the introductory course to spectroscopy. Therefore, I stopped there. Now, in the next part of this overview, there is only one more part on this. I will talk a little bit about the review of the vibrational spectroscopy that we looked at, with the more important formulas that you need to remember and you also have to keep in mind in taking this course further. So, we will move on to the vibrational spectroscopy of what is called the harmonic oscillator model spectroscopy for the diatomic molecule, and then we will also look at the summary of the normal modes that we studied, along with this one extension model for the non-anharmonic model, namely the Morse oscillator. That will be the summary of the remaining part of this overview of the whole course. Thank you.